So everyone can see my screen.
Yes, sir.
Okay then. Okay then. So if my voice is audible and my screen is visible, so we should start. So just somebody confirm that my screen is visible. So I'm presenting right now. Is it visible?
Yes, sir, it is visible.
Okay, okay. Okay, then, hello everyone. So let us start today's session. My name is Tanma Sharma. I'm a Prime Minister Research Fellow and teaching assistant appointed for this NPTEL course. So that is IC engines and gas turbines. So in the previous course, I have shown a few many videos about how the IC engines operate, what are the different cylinder arrangements, and what are the different strokes, the four stroke and the two stroke, how these operate, and what are the their indicator diagrams, the valve timing diagram. So if anyone has missed that class, they can refer to my YouTube video. So it is available in YouTube, and so I have collected a lot of videos from different sources from YouTube itself, so that it is quite convenient for you to only have one source, and you can go through all these things, and you can learn better. So in today's class, we'll be solving few problems. So this tutorial will be regarding problem solving, and we'll be solving problems related to air standard cycles, the Otto cycle and diesel cycle. Whereas I have actually covered a lot of problems of Otto cycle, but a few of diesel cycle, and let us see if we can complete till then. And in the next class, we will be concentrating again, continuing from diesel cycle, and learning about the dual cycle, solving a few problems related to that, and finally the carburation, which is the topic for the next week, right? So, so let us start. First of all, I would give you a quick recap of the spark ignition engine and the diesel ignition engine. So, spark ignition engine is so before learning about the Otto cycle, which is the air standard cycle, we need to know about the spark ignition engine, because basically, theoretically, if we want to indicate all the processes in a pen and paper, we would like to use the reference of the Otto cycle, right? So before learning Otto cycle, we should know what is a spark ignition engine, how does it work, and what are the different processes associated with it. So these are so I'm here showing a four-stroke spark ignition engine, whereas there can be two-stroke spark ignition engine as well, SI engines. And we'll be only concentrating on the four-stroke part in this course. So, and this is how, let me switch on my pointer. Yeah. So, basically, this is the cylinder arrangement, cylinder piston arrangement. So this is the piston, this is the connecting rod, this is the crankshaft, and as the piston moves up and down, it rotates the crankshaft, and as per the rotation, we will get the torque required in our the wheels of the cars, right? Cars and automobiles, any automobiles. So this is the inlet valve, this is the exhaust valve, and this is a spark plug by which we name this engine as a spark ignition engine, because the ignition of the fuel air mixture is done use of a spark produced by the spark plug. So the air fuel mixture enters, and this is the first stroke is the suction stroke, and as the air fuel mixture enters, so the piston usually moves down, it creates a low pressure than the ambient pressure, and due to this low pressure created, the charge, which is the air fuel mixture from the carburetor, it moves inside, and it occupies the volume inside the cylinder, right? And during the next stroke, which is the compression stroke, the inlet valve closes, the exhaust valve closes, and as the piston moves up, it is compressing the air fuel mixture, the charge, and accordingly the pressure and temperature are increasing. And the fuel that is used and the compression ratios in which these engines operate, these are not quite high, and these cannot self-ignite the fuel mixture. And as a result, you need an extra source of energy, that is the spark required by the spark plug, in order to ignite them. So when the compression stroke completes, when it is moving to this, the top dead center, the the pressure and the temperature are very high, and the spark plug produces a spark, and the fuel ignites, and accordingly, at very small infinitesimal change in the volume, there is a very high change in the pressure. So that's a constant, almost a constant volume process, and due to that, the cycle that we will refer, the Otto cycle, it's a constant volume heat addition cycle. So here, as the fuel will ignite, so the phase will change from the liquid phase to gaseous phase, and you will know that the specific volume of liquid is very less compared to the specific volume of this the gases, because the density of gas is very less, right? So it will have to, the same mass, it will have to spread and occupy a very high volume, and accordingly the volume is being restricted by the piston, right? So in order to facilitate a very high this occupying this volume in the cylinder, it has to push the piston downwards, and accordingly it exerts a force onto this piston. As the fuel, it spreads, it expands. So then we will have the expansion stroke, or the working stroke, in which the force, the chemical energy, getting converted into kinetic energy, and finally it pushes the piston downwards, and it rotates the crank this shaft. Accordingly, we will get the torque required in the wheels. So this is the working stroke. Only one stroke in the four-stroke engine will have a working stroke, and the rest will be only there to complete the cycle. And that is also quite important. So the entire power which is required in this, that we get in this stroke, is actually divided into all these four strokes, and we will not get exactly the whole amount which is being produced out here, because there is lubrication required, the friction required, and other this parasitic forces are also being applied over here. So again, we need to operate the spark plug, so for that also an energy will be required. So the vehicles will also have a battery, it need to charges the battery, so some amount of energy is being occupied over there. So the net amount which is produced is not getting exactly reflected onto the crankshaft rotation or the torque which we get, and so it is getting divided out here. We cannot rely on this exactly this amount. Whatever uh, fuel is burnt, that energy is produced, and that energy is not getting converted into the rotation. So accordingly, there is a efficiency. So it cannot be 100% efficient, right? So as the piston is pushed down into this working stroke, eventually again, due to the inertia of this crankshaft, the piston will move up, and this time the inlet valve is closed and the exhaust valve opens, and the piston moving up actually pushes the gases outside uh, through the exhaust valve, and so this burnt gases goes down, goes out. So that is the whole cycle. Again, when the piston comes, the exhaust valve closes and the inlet valve opens, and the mixture is sucked inside. So this is the actual PV diagram of a four-stroke Otto cycle engine. And again, let me first tell you that all these images, all this data, all the questions that we'll be solving, I'm following the book Internal Combustion Engines by R.K. Rajput. So it's quite an old book, but the problems and the explanation given there is quite nice. So you can refer to them, and it's quite easy to understand also. And I have followed this book in my previous session as well as in this session. So you guys can refer to that book. Yeah. And then coming back, so this is the pressure volume, this curve of this four-stroke engine. So in the suction, so 5 to 1 process is the suction process, and here you will see this. If this is the atmospheric line, the pressure below is below. Sorry, the suction process has a pressure lesser than the atmospheric line, due to which a low pressure zone is created out here and the fuel mixture is sucked in. Again, from 1 to 2, there is the compression stroke. So this is the compression stroke. Accordingly, the pressure is also increasing. You will also find the temperature will also increase. Then at point 2, very near to point 2, because these points are not sharp, you do not have a point of discontinuity out here. So these points are not sharp, and when it is just approaching the top dead center out here, the spark is produced by the spark plug, and accordingly uh, explosion occurs, a very controlled explosion, and the volume expands out here. But since the volume is restricted by the piston, it in turn it exerts a force out here. So the pressure you see between 2 to 3, that is when it is very near to the top dead center, so you will see that the pressure rises automatically at a very, very small volume difference. So hence we can call it as a isochoric expansion, so constant volume expansion, and accordingly the heat is added out here. So the heat added in this kind of cycles or this kind of engines is constant volume process. Then at point 3, the piston retraces back from the top dead center to the bottom dead center, and accordingly there is an expansion process, and you will see the pressure and temperature it decreases till point 4, and again from 4 to 5, the since the exit valve was closed initially, so as it moves upwards, a pressure is created which is higher than the atmospheric pressure, and due to this pressure difference, higher pressure out here and lower pressure outside, the gases are expelled out of the cylinder through the exhaust valve or the exhaust port, exhaust manifold, whatever you say, and through that the exhaust gas goes out of this cylinder arrangement. And if you have to solve it theoretically, so you will have to follow a curve like this. You cannot follow a curve like that because you cannot accommodate this kind of curve if you are going to use the ideal gas equations or other adiabatic thermodynamic relations. So in order to somehow predict how the engine is working, we need to calculate some uh, of the thermodynamic terms like work done, heat added or heat released, then efficiencies. So for that, we will follow this kind of diagram. This PV diagram actually has um, this exhaust and the suction stroke. It is minimized to a single line. Then just a minute. Mm, yeah. So again, the exhaust and the suction stroke is minimized to a line. So there is no pressure difference like this. Then from 5 to 1, the suction, then a simple compression into 2. Then we do not have a curve like this here. The spark plug ignites and the pressure and the temperature rises up to 3. And after that, at 3 point, it expansion strokes takes place. So these are sharp points. These are points of discontinuity, which is not possible in practical applications, but we will have to follow them in order to solve the problems. So next, I'll be running a video for you guys, and you will see how the engine operates and how this PV diagram is actually looks like and how it is coming into shape. So this is the video.
How four-stroke gasoline engines work. Four-stroke gasoline engines use four strokes of a piston to complete one combustion cycle. The four strokes are intake stroke. The piston moves down, drawing air into the cylinder via the air intake valves. Compression stroke. The piston moves up, compressing the air within the cylinder. Power stroke. Fuel is injected, and a spark plug ignites the air-fuel mixture, causing a controlled explosion. The expanding gases force the piston downwards. Exhaust stroke. The piston moves up, forcing the exhaust gases out of the cylinder via the exhaust gas valves. The four strokes repeat themselves over and over again, generating power, then transferring it to the load. Subscribe to our YouTube channel to learn more about engineering.
So you can subscribe to their channel. They have quite a lot of videos like this, and it will help you to understand the working mechanism of such engines. And So, have you understood? Am I audible till now, or is there any confusion? So, from now on, we will be starting solving some examples. Am I audible? Hello, hello. Am I audible? Would kindly someone respond if I'm audible or not? Just see. Okay, okay. Okay, sure, sure. But you guys can actually ask me any questions if whenever needed, you know. You do not have to just type in messages. You feel free to interact. You need not worry about anything. We are here to understand the course better, right? So yeah, feel free to interact. Okay, then I will continue. Just I'll leave it open. Huh.
How
So next, let us understand the thermodynamics behind this Otto cycle and the air standard cycle. Already, this has been covered in the course in one of the lectures in the NPTEL sessions. So, but still, I will just cover it to brush up your memory and let us see. So, Mm, hmm. So this is the PV diagram, and accordingly, you now know all the strokes. So this is the so we will just consider from one. So that is the adiabatic compression, the heat addition, constant volume heat addition. 3 to 4 is the adiabatic expansion, and then 4 to 1 is again exhaust stroke. So this is the swept volume. So the piston, so if you see this piston, so it moves from this point 1 to point 2, the volume of point 2. So that is the swept volume, whereas the total volume in the cylinder is this much. So you need some kind of clearance. And what if we do not have the clearance? So the lesser the clearance, more is the efficiency, and you will get to know about it in some time. But we need the clearance because the exhaust valve, if the piston strikes those exhaust and inlet valves, it will break the valves. So we need some small amount of clearance. For that also we need the mm yeah. So that's why the clearance volume is required, and that's a natural defect, you can say. And for that we cannot go to very very high efficiencies. So that's the thing, and this is the TS diagram. So 1 to 2, basically 1 to 2 is simply isentropic process. So adiabatic, isentropic means entropy constant. So 1 to 2, then V constant. So this is how the constant volume or the isochoric process looks like. 2 to 3, then 3 to 4 is again isentropic process of expansion. This is 3 to 4 expansion. Then 4 to 1 is again volume constant process or the isochoric process. This is how it looks like in a TS diagram. Then this is what I told basically. Again, yeah, one thing to note that in 4 to 1. So basically this is the heat rejection process also. What happens is when the gas is being expelled out of the exhaust stroke, so what happens is that the burnt gases also has a particular temperature which is not reduced to the initial temperature, right? So that's why it has some kind of enthalpy left with it, which is we are expelling out of the cylinder. So that is heat rejection. We needed that heat but we cannot get, so that is because of the efficiency is always has to be there. And if we can somehow utilize or burn the whole gases, okay, there is another problem, like some amount of gas will not burn. So that is also being fresh, not fresh exactly, but unburnt parts are also being expelled out. So that is a loss. We are bound to get some good amount of work output, but we will not get because of such kind of defects in the system. So that's where the heat rejection process takes place. 4 to 1. Then heat supply. So we will now try to get what is the formula for the efficiencies and the mean effective pressure, and we will get to know what is mean effective pressure, then work done. So these are the things which we need, and also the heat rejected at constant volume. If we know that, then we will get the overall performance of the our cylinder, sorry, the engine. So the heat supplied at constant volume, yeah, CV, that is specific heat at constant volume, T3 to T2. So we can use this TS diagram for such kind of things. So T3 to T2 at CV, so that is heat supplied, and heat rejected is T4 to T1. So T4 minus T1. That is, you can know that. And work done is heat supplied minus heat rejected. So basically, from the first law of thermodynamics, we can directly see that the work done integral, the cyclic integral, is also the heat cyclic integral, right? So you can from that you can get to know that the work done can also be calculated by knowing only the difference between the heat, that is the heat supplied minus heat rejected, that is automatically going to get accounted for the work done. Or else you can directly account for the work differently, but that is a little bit difficult. So that's why we account for the heat supplied minus heat rejected part, and this is how the relation will look like here. And then the efficiency, as we know, that is work done by heat supplied. So by plugging it into this uh, equation, so we will get this kind of relation. And again, CB all are common, and we will get finally this kind of relation. Now, this is not a very convenient relation for us. We rather want to make it quite simple, so we'll have to derive it thermodynamically. And for deriving it thermodynamically, uh, we first this define a few terms like the compression ratio. The compression ratio is basically V1 by V2. So this is the total volume divided by the clearance volume. So that is the compression ratio out here. And the expansion ratio is how much it has expanded. That is V4 by V3. So V4 divided by V3. So from V3 it has expanded to V4. That is the expansion ratio. Then we know that for the adiabatic relation, we have an expression like that between temperature and the volume. And similarly, for the process, this is for the process 2 to 1, 1 to 2, sorry, 1 to 2 isentropic compression process. And for 3 to 4, that is isentropic expansion process. And eventually, we insert the values of T2 and T3 in equation, the previous equation of the efficiency. We get such kind of relationship, and taking this common in a very simplified term, we will get the efficiency of the standard Otto cycle, right? So this is the efficiency out here, and it is completely based on the compression ratio, that is V1 by V2, or the total volume divided by the clearance volume. So just imagine, the if the compression ratio is quite high, if the R value is very high, then this part will be very less, the negative part, and in turn it will increase the efficiency of the Otto cycle, right? And for in order to have a very high compression ratio which is increasing the Otto cycle efficiency, we need to reduce this clearance volume, right? So the V1 by V2, so V2 is the clearance volume out here. If we reduce the denominator, eventually the compression ratio will be increased, and we cannot increase the total volume because we have space constraint, right? So in turn, we can try to reduce the clearance volume, but we need some amount of clearance volume in order to protect our other parts of the system, and that is cylinder head, the inlet, and the exhaust valve. So we need to protect that, right? So that's why we had a limitation, and the Otto cycle efficiency is completely dependent upon the compression ratio. So we will use this formula later in our uh, this exercises. Then the net work done per kg in an Otto cycle. So that can be given as thermodynamically, we can say, because these are adiabatic processes, right? Reversible adiabatic processes. So P3 V3 minus P4 V4 divided by 1 gamma minus 1. So that is heat supplied. So in here 3 to 4, this process, or if you look at the PV diagram, that is 3 to 4 is this process. So the heat supplied uh, during this process, I mean, the expansion, sorry, the net work done is being happening in 3 to 4, the expansion stroke, right? So yeah. So the expansion stroke, as it is pushing the piston and responsible for rotation of the crankshaft as a whole. So that is the work done, but there is some amount of work which is again needed to compress the charge, right? That is the uh, one is the work output and one is the work input that is required. So this part is 1 to 2 part is the work input. So that is how work output minus work input will get the net work done per kg in the Otto cycle. So simply multiply with that, and you can avoid this 10 to the power 2 into kilojoule, but you will have to take care of the units that you are using. So suppose P3, P2, P1, P4, these are all in bar, suppose. Then we know that 1 by 10 to the relation is 10 to the power 5 joules, 10 to the power 5 Pascal, right? 1 bar equals to 10 to the power 5 Pascal. So that's where it is coming 10 to the power 2 into again kilojoule, so 10 to the power 3, so 10 to the power 5 together. So this is what the book follows, but be careful with the units, and eventually the unit of V1 should be meter cube, and since it is per kg, so per meter cube per kg, right? So that's how the this is coming, and these are the due to the adiabatic relationship we can get this, and again simple thermodynamics we can get all that ratios, and finally we plug in into this equation like this. So we are trying to simplify the equation out here, and finally we will get a far simplified equation, but again we need in terms of P1, right? So eventually we divide it by P1 and we will get this RP P4 by P1 part, which is the pressure ratio, and accordingly the net work done per kg in Otto cycle will be P1 V1 by gamma minus 1 into R gamma minus 1 minus 1 into RP minus 1. So that's a big formula, but you can try to memorize that. So in GATE, sometimes direct questions come. And if you know the whole formula of this Otto cycle, diesel cycle, even dual cycle, I'm not sure, but sometimes such complicated questions does not come in GATE. But at least if you remember the Otto cycle and diesel cycle, this relations, so you will find very easy. You will not have to derive all this and finally come up. Your time will be saved. Then let us talk about the mean effective pressure. What do we mean by mean effective pressure? So the mean effective pressure has a particular formula, that is total work by volume displacement. And if you see in this Otto cycle, if I have to uh, get the total work, if we know the mean effective pressure, we will just multiply with the net displacement of the volume or the swept volume out here. So basically your mean effective pressure will be somewhere lying around in between, that is between the maximum pressure and the minimum pressure, usually it should be. Then the total work can be simply P into del V, right? So this is the total work actually we are getting, and that is equal to the entire work between this cycle, right? So yeah, so if you know the mean effective pressure, you need not go to the all the thermodynamic relations and everything. You simply know the geometric conditions of the cylinder, how much it is sweeping or the swept volume, and simply multiply with the mean effective pressure. So if you know the mean effective pressure, actually you can comment on the engine also. So lesser volume, in lesser volume, you will get the higher work output for the same work output. So if for a higher mean effective pressure, you will require lesser volume for the same work output to get. So that's the comment you can give by mean effective pressure, and it is quite useful. You cannot do the thermodynamic calculation everywhere, right? Then we need to finally find what is the mean effective pressure out here. So that is the net work So we already found what is the uh, work done output, everything. So that is divided by the V1 minus V2, which is basically the swept volume out here. This is the swept volume, V1 minus V2. So this is the division sign, right? So again, if we solve it, you will find the relation in the book. So if you simplify it further, eventually you will end up with a relation like this. Yeah, it's a little bit complicated, but again, if you try to memorize it, like, see, in the work done, P1 and this particular part remains constant, right? And divided by gamma minus 1 part. So eventually, if you uh, memorize as in series, like this part remains constant and everywhere, you'll find it quite easy to memorize every part of the thing. And really, to speak, this is only from the gate scoring point of view. You need not actually memorize everything. You should actually know how to derive and how to get this particular equation. So this we will also use in auto cycle problems. So later. So let us now first start with a first problem. So do you have any questions? Let me just see. Yeah. So do you have any questions? You can unmute yourself and you can speak if needed. If not, then let us continue. So in order to solve problems like this, um, the it is a very straightforward question. The efficiency of an auto cycle is 60% and gamma is given as 1.5. That depends upon the type of gas, like monoatomic, diatomic, triatomic. You must have learned in thermodynamics the gamma value. And it is asking what is the compression ratio. So for compression ratio, so we know that the uh, the auto cycle efficiency is 60%, gamma is 1.5, and we also know that the efficiency of the auto cycle is given by this expression out here, 1 minus 1 by r to the power gamma minus 1. We know everything, I think, in fact, what is r, we do not know. And from that, by solving, we can find the value of r as 6.25. So that is basically the compression ratio. That is the difference between the pressures in compression. So P2 minus P1, sorry, V2 divided by V1. Uh, yeah, sorry, the total volume divided by the clearance volume. So V1 divided by V2. Sorry, yeah, the opposite I said. And that is 6.25, you can see. So if you remember in the classes, the compression ratio for um, gasoline engines is lesser than that of diesel engines. Like for gasoline engine it is like 6 to 8 to 12 or 8 to 10, sorry. And for diesel engines it is 16 to 22, the compression ratios. And higher compression ratios is required in the diesel engines because there the fuel has to ignite on its own and there is no requirement of the spark plug. So that's why the compression ratio is quite high. And you will find we will also derive how we can get the compression ratio thermodynamically in there. And eventually, um, depending upon the cycle, we will get a very different expression. But we just need to know that the compression ratio, for if it is given for auto cycle, if we get in the range of around 10, then our answer would be quite correct. So that's a method of evaluating yourself while doing the problems. If you're getting very low compression ratios, then I think you need to recheck your calculations. If you're getting very high, suppose like in range of 20s, but it is an auto cycle, so you need to again use your logic that yes, this is a auto cycle, the compression ratio should not be that high, so I need to recheck my answer. So that would actually give you confidence in your solution. Then let us move on to the next problem. So we will see these problems that engine, the geometric configuration is given like the engine has a bore or the diameter is around 250 mm, and the stroke, that is the length up to which it works, is um, 375 mm, right? So the amount of volume, the total volume of the engine is given. So we know by that what is V1, right? The clearance volume is 0.0263 meter cube. So we know the VC. So we will eventually get to know the VS. Then the initial pressure and temperature are 1 bar and 50 degrees Celsius. So here at this point, where the pressure is 1 bar and 50 degrees Celsius. Here the maximum pressure is limited to 25 bar. So the P max out here at point 3 is limited to 25 bar. And practically, if you see why such limitations are required, is that the material of this cylinder, by means the from manufacturing point of view, may has a particular limit which is not too far away from the pressure and the temperature within the cylinder. So that's why, in order to not harm the cylinder material, we need to limit the pressure, that is the P max. So that's why the maximum pressure is limited to 25 bar. So we need to find the air standard efficiency of the cycle. That should be quite easy. And the mean effective pressure of the cycle, assuming the ideal conditions. So these are the conditions given. I have listed down, and you will find that, as per my experience, so during evaluating, during calculating or solving these kind of problems, if you somehow make a list of all the parameters that are present, and somehow you are able to calculate all the temperature and pressure points at this 1 2 3 4 points, then you will simply, you can solve without any uh, at a very less time, and also without any uh, point of mistake. So that's why it's a good habit to first list down all the things that you have in your hand. So the swept volume we can directly get as a pi by 4 d square L. So you have the D and you have the L. Accordingly, the swept volume is 0. Uh, so let me see. This is a 250 mm bore and a 375 mm stroke. So if this is stroke, it is not the entire cylinder length. So that's why you directly use the L as 375 mm here. But if you are given the entire cylinder length, that is from the piston head to the bottom dead center, that would mean differently. So you will not get the stroke. So here actually you are getting the stroke volume Vs directly, and you are given separately the VC. Accordingly, you will get the total volume. So what I commented earlier, that is not correct. So we do not know the V1 from this top statement. We rather know the Vs till which the piston displaces. So that's swept volume, and we get the compression ratio R as Vs plus Vc divided by Vc, that is 8. And if it is an Otto cycle, I think the compression ratio works quite fine. Then the air standard efficiency simply works on the compression ratio. So that is given by this formula out here. And so this, by solving, you will get, this is 56.5% efficient. But again, air standard efficiency is a theoretical part. There are a lot of errors, there are a lot of losses during the practical evaluation of this whole cycle, and such high efficiency is generally not reached. So the efficiency of the actual engine, which is represented by this air standard cycle, is very less. The actual efficiency is very less. So the mean effective pressure, we just calculated it. So that is given by this relation. And here the RP, the pressure ratio, that is P3 by P2, we do not know. P3 or the value of P3 and P2. So we'll have to find out thermodynamically what are these values. And first, let us consider the process 1 to 2. Why we have considered this as first? Because we know the starting condition P1 and P1, right? So extrapolating from here to point 2 and then from point 2 to point 3, we'll get the finally all the values of P3 and P2. So from here, if we use the thermodynamic relationship of a adiabatic process, so this is what we will get, and solving it, we will get 18.38 bar. So V1 by V2 terms come, and this is V1. So from here to here, that is the total volume divided by V2. So V2 is the clearance volume. So total volume by clearance volume, that is the compression ratio, and eventually the P2 turns out to be 18.38 bar. So at 18.38 bar, the ignition, the spark plug produces a spark and the ignition takes place, and accordingly the pressure will rise from P2 to P3, and we'll have to find out what is P3. So RP P3 to P2 is 25 divided by 18.338. So we were quite lucky in our case that the maximum pressure is already given. So that is 25. And accordingly, the pressure ratio is 1.36. So the mean effective pressure, now putting in the values of R, RP, P1, everything. So we will get that to be 1.334 bar. That is the mean effective pressure. So you can have a look at this procedure, although you can also find this problem in the book by internal combustion by R.K. Rajput, the internal combustion engine. So here the example is 3.8. You can go back and look at this part, and there are a lot more problems in the book. And yeah, by the way, I will be covering a lot. I will be solving some very peculiar type of problems, so that which may actually crunch your brains, really, because in practical scenarios, studying an engine is very difficult, and we will somehow try to go a level up in each of the problems, and accordingly we will find that we know the IC engines quite well. So this is one of the problem. Then let us go to the next, which was a gate problem at 1998. So what is given out here is that the minimum pressure and temperature in an Otto cycle are 100 kilopascal and 27 degrees Celsius. So at pressure and temperature at 0.1 is given. Then the amount of heat added to the air per cycle is 1500 kilojoule per kg. So amount of heat added 2 to 3. We know that now. So we need to determine the pressures and temperatures at all points of the air standard Otto cycle. Also calculate the specific work and the thermal efficiency of a cycle for compression ratio of 8 is to 1. So we know the compression ratio also now. So let us first find out the pressure and temperatures, and I will show you how to find it out. And we will use 1 kg of air in all our calculation, and later we can only multiply with the mass of air to get the exact value, but we do not have to do that in this case. So this is where all the points are listed. First, let us consider compression process 1 to 2 in order to find the values at point 2. So we just use the simple adiabatic relation, and T2 by T1 equals to V1 by V2 to the power gamma minus 1. V1 by V2 we know is the compression ratio, just as indicated in the previous example also. And then we will get the T2 value is 689.1 Kelvin. So just mind, there is a very frequent mistake that is found in these kind of problems. So each of the problems, you need to convert the degree Celsius or degree Fahrenheit, whatever the unit, back to degree Kelvin. If not done, then your answer will be incorrect. So that's why you see T1 equals to 27 plus 273, that is 300 Kelvin. So you need to do that, and accordingly you will file ease also. Then for pressure part, if we have this relationship, we will finally get the P2 equal to 18.379 bar. So we know now P2 and T2. Let us now solve for the point 3. And for that, we will use the constant volume process. Now, thanks to the problem that we know what is the amount of heat added during this process, that is 1500 kilojoule per kg, right? So for 1 kg of this gas, we know that CV into temperature difference. So that will be around 1500, and accordingly we now know T2, we know CV, so we can directly find T3, right? That is 2772.4 Kelvin. So from 689 it has moved to 20 around 2800 Kelvin. So you see how much is the pressure, how much is the temperature rise, and you will also get to know what is the pressure rise out here. So for an isochoric process, so 2 to 3 is a constant volume heat addition process, so it is an isochoric process. You from ideal gas law you can find this relation, so you will get to know the value of P3 to be 73.94 bar. So from 18 bar it is going to 74 bar around, and again there is almost 4 times increment in the temperature. So you see how much pressure and temperature rises during the heat addition process. Then we need to solve for uh, just a minute. So now we will be solving for point 4, that is through adiabatic expansion process 3 to 4. So T3 by T4 equals to V4 by V3 to the power gamma minus 1, and accordingly this we know V4 by V3, so V4 by V3, right? So that is since this volume are constant, so V1 equals to V4, and 2 to 3 also it is a constant volume process, so V2 equals to V3. So we can simply see that it is a relation similar to V1 by V2. So that is, we know that is the compression ratio, so we simply plug in the term of the compression ratio and we get to know um, uh, this is the value of the ratio. Then T4 can be given by this expression, that is 1200 Kelvin, around 1200 Kelvin. Then for the adiabatic process, by similar means, we can find, so V3 by V4 again comes into play, so that is 1 by 8 to the power 1 by 4, and that is 4.023 bar. So for point 2, 3, and 4, we have now calculated all the pressure and temperatures. So this is how you will be needing to calculate all the pressure and temperatures. So somewhere, some point, you'll be given a hint about the point 3. So this is not a normal process. The hints are given like the point 1, that is the inlet condition, or this the first starting condition. So the air, normal ambient air temperature and pressure is the value at point 1, right? So from that we will manipulate the thermal properties of the air, and because since it is not air fuel mixture, it is simply air cycle, right? Then we'll be compressing, then expanding. So that will be done through the air, but the starting point is that of the ambience. So that is one hint. The second hint will be given for point 3. So if you know what is the value of point 1, you will know the value of this point 2 through the simply adiabatic relationship, but you cannot get to know about the point 3. So you will have to get a particular hint from the question. So that's my point for that, why I have selected this question out here. Then we need to calculate the specific work and the thermal efficiency. So the specific work and the thermal efficiency, first we calculate the specific work. So that is heat added minus heat rejected. That will be quite working simple for us rather than using a very big equation, right? So if we know the points, all the points, everything becomes simple for us now, right? So by solving this, CvT3 minus T2, CvT3 minus T2, that is heat addition, minus CvT4 minus T1, that is heat rejection. That will eventually give a net work done or specific work is 847 kilojoule per kg. Mind you, what is specific? Why not work output? So the term specific comes because the work output is in terms of kilojoule per kg of gas. That is specific to only 1 kg of gas. And if you have a higher amount of gas, then this value will get scaled up or scaled down, whatever may be the case. So that's why we calculate the specific work. Then thermal efficiency, we know, we have derived previously. Simply we know the compression ratio, so we need not find all the points for that, and we will yield up compression ratio of 56.47%. This is the next problem, but before that, let me ask if all are able to follow me. So is there any question? I can take questions. If there are no questions, I should proceed to the next question of my own. So, air standard Otto cycle has a volumetric compression ratio of 6, the lowest cycle pressure of 0.1 megapascal, and operates between temperature limits of this. And so that you get the hint of this 0.1 as well, this 0.1 and the 0.3, right? So, mm, yeah. So you get the hint of 0.3 and 0.1, and you need to calculate the temperature pressure of the isentropic expansion. So isentropic expansion is this fourth position. So for that, you need to find, actually you will have to go through all the points here, and same way for process 1 to 2, you know the points of 1, you can calculate the thermal the properties of point 2. So this is how you will do. The temperature at 2 will be known to now, and the pressure is 12.3 bar. Then for the constant volume process, for 2 to 3, we now know the temperature. So that way we can calculate what is the pressure at this particular point. And for the expansion process 3 to 4, so 3 to 4, so this is the adiabatic thermodynamic relationship. Then by this we will get to know what is the temperature as well as what is the pressure at this particular point. The second point is a little bit tricky. Now the second is, since it is observed that the values in 1 or the part 1 are well above the lowest cycle operating conditions, the expansion process was allowed to continue down to a pressure of 0.1 megapascal. Which process is required to complete the cycle? So here, if the process 0.4, here it is allowed to expand, it will go on through this curve and it will somehow lie at this particular pressure point. So suppose we have a particular line out here, and this line extended will somehow intersect out here. So it is allowed, the expansion process was allowed to expand up till this pressure, right? So this is the point, new point now, and then it has again come to 1, right, through the compression process. So what kind of cycle it can be? So the cycle is called as the Atkinson cycle, and you will have to supply a constant pressure scavenging. So what is constant pressure scavenging, right? So basically this is a new cycle. So zero point 0.4 was the initial condition, and from that it was allowed to expand up to 0.5, and where it is now in sync with this one thermal properties. Now there is a slight problem in this figure. So the 0.1 is having a pressure of around 0.1 this megapascal. So 1 is having 0.1 megapascal, and the 5 is also after expansion till zero point 0.1 megapascal. So these are lying in the same line actually. Although it is the figure has a certain mistake out here. So this 5 to 1 process will be a constant pressure scavenging, means you will have to release the gas from the exhaust valve. So that is you will have to do, and again in the same way you will also have to extract the this um, the new the fresh charge. So in that case, sometimes what happens is that the fresh charge also gets mixed with the unburnt gases and sorry, the burnt gases in the previous cycle, and both the fresh and the burnt gases mix and go out through the exhaust valve. So that is not available for the combustion. So if that happens, then it is called as the scavenging, and this constant pressure scavenging needs to be done. And accordingly, you will find that since we are now expanding to a very long process, it will be beneficial for that. So this is constant pressure scavenging. Just a minute. So is there any question? So you can ask me this question that why this uh, this Atkinson cycle, if it is present and it is working well, why not we use that instead of the Otto cycle? So I leave this question up to you to find out from the internet, whichever medium you want to, and you get the answer that what is the advantages and disadvantages of an Atkins cycle. Why not use an Atkins cycle instead of an Otto cycle? So in that you will have a longer time of expansion stroke, and expansion stroke means the work being transmitted up to the this crankshaft. Yeah, this is the working stroke, right? So longer the working stroke, more the power being extracted out of it, more would be the efficiency, right? But still, what is the disadvantage of an Atkinson cycle? Why not we use it instead of an Otto cycle? So you kindly go through it. All the processes have its own um, this advantages and disadvantages. So you need to be aware of that. So next, this is the constant pressure scavenging, and let us see how it has increased the efficiency, right? So the for an Atkinson cycle, the efficiency is given by the same expression, work done by heat supplied, that is heat supplied minus heat rejected by heat supplied. And through the thermodynamic relationship, we can see that now heat rejected would be a constant pressure process, right? So nowhere we need to have a CV now. We need specific heat at constant pressure. So that's why we are having CP, and T5 to T1 is the temperature difference. So Cp into delta T is given as a heat rejected. So this is a difference. Normally, in the previous case of Otto cycle, we had a Cv into delta T because the heat rejection was in constant volume process, but now the heat rejection is constant pressure process. That is the difference between the Atkinson cycle and the Otto cycle. If asked, you can directly say that. So in Atkinson cycle, heat rejection is constant pressure process. So you see 5 to 1, and in yeah. Is there any question? Hello, was there any question? Okay, then I will move forward. So yeah, I was saying that the difference between Atkinson cycle and this Otto cycle. So in Otto cycle, constant volume heat rejection, whereas in Atkinson cycle, that is constant pressure heat rejection. So eventually, we will get this kind of relationship. Cp by Cv is gamma. We know that, and if we solve it by adiabatic this process thermodynamic relationship between T5 and T3, so T5 to T3, so this part, whole expansion process 3 to 5. So by that we will get to know about the T5, which is we will plug in here. T3, T2 and T1 we know already, and eventually we will get Atkinson cycle this efficiency. So the main advantage is that this gamma being added out multiplied to this part, right? So th- uh, that is how it is getting increased, and you will see that although the gamma being added out here, you will ask me this question that minus negative part is now being scaled up, but that is not the case. The difference between the temperature, so here you find the T5 minus T1, so T5 minus T1, eventually the T4 minus T1 would be a little bit different than T5 minus T1. Accordingly, not only the gamma is affecting, but the temperature differences are affecting. That's why the overall case is Atkinson cycle has a higher efficiency of 59.29 and Otto cycle has a 51.26. So you find the answer. Why not use an Atkinson cycle? Why use an Otto cycle? In which cases it is possible, and you will be a little bit more aware of in this course. So 8.13% improvement in efficiency. Now we have solved a lot of problems of Otto cycle. Just will see once before starting the. So if any question, I can take questions now. We can interact. We have a lot of time, or I can go ahead and finish today's session. There's no issue. Okay, then I will go ahead. So we will now focus into combustion ignition engine and try to find the thermodynamic relationships of the A standard cycle associated with CI engine. So before going to the air standard cycle of CI engine, which is the diesel cycle, let us talk about what is a combustion engine, combustion ignition engine or a CI engine. So very same representative as the previous, that is the spark ignition engine or the SI engine. So in a CI engine, only difference is the fuel injector is present in the case of spark plug, and fuel is directly injected inside the cylinder, whereas in spark ignition engine, the air fuel mixture is supplied inside the cylinder. So that's the main difference between that, and the process of ignition is that's why different. What happens is that very similar as the piston comes down, there is a low pressure out here, and due to which the air, only air gets sucked in, and accordingly in the compression stroke the air is being compressed at a very high pressure and temperature, and at this high pressure and temperature it is very sufficient to ignite the fuel which is being used here, that is diesel, and the diesel fuel is directly injected into this chamber here, right at the end of the compression stroke, and this fuel when it comes out of the nozzle, you will find later, you will get to know in this course that this fuel is in mist form, not in very big droplets that you see from your taps. No, that is not the case. It is very, very fine droplets, all called as mist, and that is the process is called as atomization. And this atomization is really very important in order to ignite the fuel very fast and to reach very high pressure and temperature at a very slow time. That's why atomization process is very important, and the design of a fuel injector is of very high significance, and you will get to know how to design a fuel injector later, how the fuel injector works. So this is where the charge is now ignited, and accordingly it exerts pressure onto the piston and the piston comes down, and this is the exhaust, this is the working stroke. As the piston comes down, it is responsible for rotating the crankshaft, and finally the energy is being transmitted to the rotation of the crankshaft, or the torque is being transmitted to the wheels of the car. Then in the last stroke, the exhaust stroke, we will have to expel the gases out of the cylinder. So exhaust valve opens and the exhaust gases are moving out from the cylinder as the piston moves up. So here the energy which is being still not utilized completely by the piston or the rotating the crankshaft, the thermal energy or the hot gases, it moves away. So if the hot gases, the temperature were reduced to the ambient temperature, right, then all of the energy would have used up in the working stroke, but that is not the case. There is some heat rejection, so we'll have to live with the heat rejection. There's a you cannot avoid it, so there is a efficiency associated with that. And this is the actually how the cycle looks. So here what happens is the pressure, the injection of the fuel inside the cylinder is such that the pressure built up due to the expansion of the gases is remaining almost constant. That's the case. You will see that this curve 2 to 3, this remains almost constant, whereas in the case of uh, SI engines, the pressure builds up. So just when it reaches the top dead center and it starts to move uh, below, means to the bottom dead center, only that when the fuel injector injects the requisite amount of fuel and the ignition takes place. And accordingly, um, you will find the pressure remains almost constant, whereas the volume is increasing. And finally, you will have a working stroke. So talking from the start, 5 to 1 is the suction stroke, wherein the pressure is lower than the atmospheric line, hence the air is sucked in. Then 1 to 2 is the compression stroke, and where the air is compressed, and just when the air is compressed to the maximum pressure and temperature, not maximum, the high pressure and temperature point in which the fuel can automatically inject within the pressure and temperature combination. So when then the fuel is injected, it ignites, the pressure remains constant, whereas the um, volume, it starts moving. So the piston moves this way, right? So the volume, it starts increasing, this part it starts increasing, and accordingly after that you will have a complete 3 to 4 expansion or the working stroke. And 4 to 5 again is the exhaust, wherein you will have to have a higher pressure here in order to expel these gases out higher than the atmospheric light pressure. So this is the actual PV diagram of a 4-stroke diesel cycle, whereas this is how the theoretical cycle looks, and this is easy to interpret and easy to derive the thermodynamic relations and everything. So that's why we will follow this cycle. And this cycle, if we use with just air, we do not have to so this cycle is still not an closed cycle, or this is means the same amount of the gases are not conserved and not rotate, means cyclically not used. So that's why we need an air centered cycle wherein the cycle is closed. We do not have this exhaust and the suction stroke, and the same air is circulated throughout the whole cycle. So this is just a replica of the air standard cycle, which we will see next. But this 5 to 1 or the 1 to 5 will not exist in the air standard cycles. So this is how the theoretical PV diagram looks like. 2 to 3 is the pressure, um, this constant pressure heat addition process. 3 to 4 is the working stroke or the expansion stroke. 1 to 2 is the compression stroke, and you will find that the maximum pressure is being reached at the end of the compression stroke, where it remains constant. So next I will play a video of the diesel cycle, how it works, or the combustion ignition engine, how it works, and you will find whatever I have said is actually matching, and this is how it works, right?
How four-stroke diesel engines work. Four-stroke diesel engines use four strokes of a piston to complete one combustion cycle. The four strokes are intake stroke. The piston moves down, drawing air into the cylinder via the air intake valves. Compression stroke. The piston moves up, compressing the air within the cylinder. Power stroke. Fuel is injected and the air-fuel mixture ignites due to the increased pressure and temperature within the cylinder. This causes a controlled explosion. The expanding gases force the piston downwards. Exhaust stroke. The piston moves up, forcing the exhaust gases out of the cylinder via the exhaust gas valves. The four strokes repeat themselves over and over again, generating power, then transferring it to the load. Subscribe to our YouTube channel to learn more about engineering.
Okay, then is there any question? So next we are going to derive, to recap the concepts, we will need to derive the air standard cycle, diesel cycle, the thermodynamic expressions of work done, then mean effective pressure, then the isentropic efficiencies. So before that, I will take questions if there are any. I will just look at this. Okay, then if there is no question, let us move forward and quickly end this session. So very similar to that of the Otto cycle that we have discussed, so I will not take much time out here. The heat supplied is this constant pressure process now. That's why we use the Cp and T3 minus T2 out here. Heat rejected at constant volume is T4 minus T1 out here. It is still constant volume, whereas the work done can be given as the heat supplied minus heat rejected. So this is the expression. And next, the isentropic diesel efficiency is work done by heat supply, and accordingly, if you solve, you will get this temperature based relation with gamma coming up in the relationship. So that we need to eliminate all the temperature terms, and we need to get something uh, quite comprehensible for us, like using the compression ratio R and the cutoff ratio rho, which is the volume at cutoff divided by the clearance volume. And we will use these things because, see, we know the cutoff ratio at which, that is the interval between the supplying means the fuel inside the cylinder, and we know that part, we are governed by that part, and the compression ratio, that is the depending upon the geometry of the cylinder. So that's why we rely on these terms rather than the temperature terms, which we do not know. We actually need to know that. So that's why we will derive a formula in terms of compression ratio and cutoff ratio, and we will use the adiabatic thermodynamics expression. So this is the thermodynamic expression of the adiabatic process, T2 by T1, V1 by V2. So V1 by V2 is the compression ratio R, and accordingly we will get a very simplified term. And then again we get T3 in process 2 to 3, that is a constant pressure process. So this is the relation of the constant pressure process, and accordingly we get the value of T3. So T2 we got, T3 we got, T3, T2 we got, so we need T4 and T1. So adiabatic expansion 3 to 4, we take 3 to 4, and eventually, so yeah, so V4 by V3, V4 by V3, we can reduce it like this. So V4 by V3, uh, we simply this change it in terms of R and rho. That can be done as shown here, and you will finally get the value of T4 in terms of T1, that is rho to the power gamma. So next, the eta diesel, finally, if we plug in all the values or expressions of T4, T1, T3, T2 in a common term, we'll finally get a relation like this. So this is the one of the final relations of isentropic efficiency, air standard efficiency of the diesel cycle. And next, we can write it like this, and if you remember this efficiency, it will be very great, because the direct questions can direct means come in the gate exam, and you will be very surprised that how much time it has saved you only by knowing this equation. Then if you compare it with the Otto cycle, so the factors which are determining this, like the determining the efficiency, are, for Otto cycle only the compression ratio is important, whereas in diesel cycle the uh, cutoff ratio is also important, and this is scaling up this negative term, as you can see. So this negative term is a little bigger for the same compression ratio R, so the efficiency is less in the case of diesel cycle. So if we have same compression ratio, this negative term is being scaled up, and that's why it is having lesser efficiency. And so this is one of the very common questions. So for a given compression ratio, you will find that Otto cycle is more efficient. The efficiency of Otto cycle is higher than the diesel cycle. So you should keep that in mind. Then the network for diesel cycle can be expressed in terms of PV as follows. So this is simply um, adding the work done by all. So this P2 V3 minus V2. So P2 V3 minus V2 is the work done out here first. Then P3 this is the expansion, which is the having the maximum work done. So that is P3 V3 minus P4 V4 divided by gamma minus 1, and that is P2 1 to 2 process is P2 V2 minus P1 V1 divided by gamma minus 1. So that is the net work done. Next, if we solve with some simplifications like thermodynamic relations, I will not go through all these. Finally, you will get a relation like this. So in terms of P1 V1, you will get a very big relation like this. So it is not generally possible to remember this kind of information. Only the efficiency part is sufficient. So if you can just remember the efficiencies of Otto cycle and diesel cycle, whereas you need to derive this if needed. And the best way you can do is that simply if you know the thermodynamic relationships of all the processes, you find the points, the temperature and pressures at all the point 1, 2, 3, 4. Then you can directly simply calculate the work done based on that. So that's not a big thing. Then the next mean effective pressure, we can simply divide it by the volume displaced, the net work done divided by the volume, and we will get a mean effective pressure like this. So let us directly move on to a question. We have only two questions left for this session, and this will be a little bit quick. So a diesel engine has a compression ratio of 15 and heat addition at constant pressure takes place as 6% of stroke. Find the air standard efficiency of the engine. So that is a very straightforward question, and the compression ratio is given as 15. You can see here. So for air at 1.4, the air standard efficiency of diesel cycle is given by this relation, which we have recently seen how to derive. And you can again go back and see this video or the refer to this book. So if we know here, we know only the value of R, but how to find the value of this cutoff ratio, right? V3 by V2. So for that, we will consider the process V3 2 to 3. So V3 minus V2 equals to 6 by 100 of Vs. So why we know that? So heat addition at constant pressure takes place at 6% of stroke. So heat addition at constant pressure. So this is 6% of stroke, this part. So that's why we considered this Vs, and later on if we calculate what is Vs, that is V1 minus V2 from this diagram, V1 minus V2, and finally we get this kind of expression, V3 between V3 and V2, and eventually by dividing it we get the cutoff ratio is 1.84, and putting the value in this equation we will finally get the efficiency of diesel cycle to be 61.2%. So that is how you should do it, and I will not solve very we have only one question, but that is a very theoretical question. We will solve very long questions in the next session, and previous session about the diesel cycle. So this is how you should be doing solving the short questions, and just have to know the correct values which we need to find, and if you know those values you can directly find that. So for me it helps if I list down what the values I have been given, and what the values I need to find. Accordingly I will select the shortest way to find those values, and because I know what the values I have been given. So next question is that for the same compression ratio, show that the efficiency of Otto cycle is greater than that of the diesel cycle. So if you need a very concrete explanation of why the for the same compression ratio, the efficiency of Otto cycle is greater than that of the diesel cycle, I've shown you that it is greater, but I have not given you a concrete explanation. So we are now given, we know these are the efficiencies of Otto cycle and the diesel cycle out here. This is the Otto cycle and this is the diesel cycle. Then as the compression ratio is same, so in these are the two cycles. So this is the Otto cycle and this is the diesel cycle, and just the processes are one in one it is dashed for the diesel cycle, in one there is no dash for the Otto cycle. Then this is the cutoff ratio of for the diesel cycle, and V4 dash by V3 dash is the compression ratio, and so R1 is equal to R, that will be the case. No, R1 divided by R is not the case, but eventually we will find how it affects. So putting the value of rho in eta diesel, we get this expression. So it's a little bit complicated, you can see here. From the equation, we observe that R by R1 is greater than 1. So R by R1. So R is basically V1 by V2 and V1 dash by V2 dash. So V4 dash by V3 dash is what? So V4 dash by V3 dash. So yes, V3 dash is a little bit greater than V2 dash. So obviously the ratio between V4 dash and V3 dash is lesser. That is R1 is lesser than R. So eventually R by R1 is greater than 1. Yes. So now we will just suffice that R1, how much it is lesser than R. So we will just give a value delta. So delta is a very small quantity. Okay. So by then, if we solve R by R1, then we will find R by R delta equals to, you will find a quantity like this. So we are still trying to find how Otto cycle and diesel cycle are having different values of um, efficiencies for the same R value, that is compression ratio. For that, we have now compared the R1 and R by introducing term delta out here. So 1 minus delta by R to the power minus 1. Finally, this can be expanded in a series expansion with this kind of equation, and you will find that if this can be expanded in this way, similarly R by R1 to the power gamma, when it is scaled up to gamma, can be expanded in a similar fashion like this. So this is simply series expansion. You can read about it, and eventually if you put in these values in the equation of diesel engine, you will find that the denominator part and the numerator part are different, and the numerator part are scaled up by this particular value, that is gamma plus 1 divided by 2, and due to which the numerator is always greater than the denominator. So this ratio is always greater than 1, right? And if you just ignore this ratio, you'll find the rest of the thing is similar to that of the uh, Otto cycle efficiency, right? Only this part is getting scaled up now because the numerator is always greater than the denominator, and accordingly the negative part is getting scaled up. So for the same compression ratio, the diesel engine will have a lower efficiency. So that's the whole way how you will have to explain how for the same compression ratio the efficiency of Otto cycle is greater than that of the diesel cycle. So that was all for today's session. So if you have any questions, I'll be happy to take the questions. Cutoff ratio, right? So cutoff ratio, let me explain. Actually, you can turn on your mic if needed. Cutoff ratio, cutoff ratio. So you see the cutoff ratio out here. So this is the cutoff ratio. Now cutoff ratio is equals to V3 by V2. So here volume at cutoff. So from point 2, what happens is that from 1 to 2, the cylinder was the volume inside the cylinder was increasing, sorry, decreasing as the piston was compressing the air, right? So you see from 1 to 2, the volume was decreasing and the air is getting compressed. So the pressure increases at point 2. And at point 2, the fuel injector, it releases a certain amount of, very calculated amount of fuel inside the cylinder at a very small space, right? In atomized form, and it will keep on supplying the fuel until point 3, right? So until point 3 it will keep on supplying, and 2 to 3 is the fuel supplying time. You will see that this is a very big part, but no, that is not. In one of the questions we already see that this part is 6% of the entire stroke, 6% only, or it can be like around 1 by 20, 20th time. So for this small duration, uh, the fuel will be supplied inside the cylinder, and 2 to 3 is the fuel supplying time. So volume at the cutoff, so this is V3 here, so that is meant by this, and the clearance volume V2. So V is this. So before supplying and after supplying, you can understand by that. So after supplying is 3, before supplying is 2. That is the cutoff ratio out here. So is that clear? So I hope it is clear. So if there is any other questions, then please, I'm here. Or okay then. Okay, Hemanathan. Thank you for your question. Thank you for listening. I think if there's no other question, then I will end this session. Thank you everyone for attending this session, and hope to meet you this Saturday from 4 to 6. Okay then. Bye bye.